Alright, in Part D, we're asked to use the series found in Part C, which is above in purple, to find a rational number a such that the absolute value of a minus ln of 5 over 4 is less than 1/100th and justify your answer. Well, you should note that when you see this kind of construct, an absolute value of some kind of difference with a less than, with an inequality like that, it usually means an error tolerance. And we have in this case we have an estimate and there is an actual value, and we will tolerate the difference between the actual and the estimate as long as it's less than 1/100th. So if that's the case here, we need to identify which of these is the actual. Now, since we were working with ln of something, you might see that ln of 5 over 4, because we would have no way to really estimate that would be an actual value. Ln of 5 over 4, we have to somehow fit it into that ln of 1 plus x squared that we've been working with. So if I call a the estimate and ln of 5/4 is the actual, which is unfortunate that they used a to be the estimate, but we need to find a way to write ln of 5/4 as ln of 1 plus something squared. Well, we might see first that ln of 5/4 is really ln of 1 plus 1/4, and that 1/4 is actually 1/2 quantity squared. And so that tells us in this case that our x is really 1/2. Alright, so that's going to be something that's very important here. Now, we're trying to work with the error of an alternating series. So alternating series behave differently than the error for an alternating series behaves differently than the error for a standard typical type of Taylor series. And if we recall the alternating series test, there are three criteria that an alternating series must meet in order to be convergent. And the first is that it must be strictly alternating. Now that's pretty easy to see. It should either be positive, negative, positive, negative, positive, negative, or negative, positive, etc. It can't be positive, positive, negative, negative. It must be strictly alternating. Second of all, the terms should be getting smaller in size. So a sub n plus 1 should be less than a sub n. That is, their absolute value should be less. Now if you look at our particular thing here, seeing that x is equal to 1/2 is going to make that true. For example, if we were to plug in x equals 1/2 and write a few terms out, the first term would be x squared, which is 1/2 squared is 1/4. The next would be 1/2 to the 4th, which is 1/16 over 2, which is 1/32. The next would be 1/2 to the 6th power, which would be 1 over 64 times 3, which is 1 over 192, etc. And so you can see that it definitely is the terms are decreasing in size. And the third criteria is that it has to pass that nth term test. So the limit as n approaches infinity of a sub n has to equal 0. And I think you can see that in this case that will also happen. I mean, the fact that they're getting smaller almost always indicates that the limit is approaching 0, but they could be getting smaller and approaching a non-zero limit. So we do have to check all three of those things. Once that's the case, we know that the alternating series converges. And furthermore, we know that the magnitude of the error will be less than the magnitude of the first unused term. So that's a lot simpler than the Taylor error. Now what I've underlined in purple there is the magnitude of the error, including the absolute value bars. And since that has to be less than 1/100th, we go to our terms and try to find the first term that has a magnitude less than 1/100th. And I already wrote them out over on the left, and that would be the third term, which would mean that our estimation comprised of the first two terms, and that sum would be a, and that would be the value that we're looking for. So when we estimate ln of 5/4 using the above series and only two terms of that, we will have an error less than 1/100th.